Okay, working through question 9b on exercise 6e. Now, the nice thing about question 9b is you don't actually need to use the information from part A to work through it. Let's just write down the information that we have. So we've got circle C1 has got a centre at -2,5 and a radius of 7. And we've got circle 2 has got a centre at 12,5, and we're told in part B that this has now got a radius of 16. We need to find the coordinates of the intersection points. So immediately when we think of intersection points, we should be thinking of simultaneous equations, finding the points that work simultaneously for both sets of graphs. So we solve them simultaneously. But we need some equations first. So let's write down our circle equations for each of these circles. So we're going to have x plus 2 all squared plus y minus 5 all squared is equal to 7 squared, which is 49. We're then going to have x minus 12 all squared plus y minus 5 all squared is equal to 16 squared, which is 256. Now, how do we solve a couple of circle equations simultaneously? Well, usually with a bit of difficulty, but it can be done. When we think of solving simultaneously, we either think of through elimination by adding or subtracting the equations together, given certain conditions, or by substituting one equation into the other. Now, it's worth being mindful in this special situation that each of our equations has got y minus 5 squared, which is quite a unique situation. It doesn't always happen with circles. Why is that an important detail? Well, you can either actually approach this through elimination or substitution. I'm going to approach it through elimination. If I consider these as two equations, so let's call the top one equation 1 and then equation 2 below. If I do equation 2 subtract equation 1, so I am going kind of in reverse with my subtraction only because I've got 256 on the bottom and 49 on the top. I'm actually going to end up eliminating my sets of brackets involving y minus 5 squared. What I will still have, however, on the left hand side, I'm going to have the x minus 12 all squared, subtracting the bracket above it, which is x plus 2 all squared. And on the right hand side, I'm going to have 256 subtract 49, so that is 207. So all of a sudden I've now got an equation that only involves x but doesn't involve y. As I say, very convenient that we have two sets of brackets identical in our circle equations of y minus 5 all squared. Now, if at this point you wanted to pause and have a little go at getting the coordinate points where they intersect one another, by all means do so. Otherwise, I'm going to continue working through this. So now expanding our two sets of brackets, we are going to have x squared minus 24x plus 144. Subtract, now I've got to be a bit careful here because I'm subtracting all of the second set of brackets all squared. So I'm going to work out what the expansion is going to look like and subtract all of that. So x squared plus 4x plus 4, that's all equal to 207. And then removing the square brackets. So I'm going to be subtracting the x squared, subtracting the 4x, and subtracting the 4. Okay, collecting everything together, the x squareds will cancel one another out. I'm going to have a minus 28x, and I'm going to have a plus 140 is equal to 207. Okay, subtracting 140 from both sides, that's going to leave us with 67. And then divide through by negative 28, not the nicest division in the world. So it's going to give us 67 over minus 28. With the minus in front of the 28, you can just pull to the front, so it's in front of the whole fraction. So negative 67 over 28. Sadly, it can't be simplified. It's not the nicest fraction in the world, but that is what we're going to end up with. I'm just going to do a double check, make sure my answer matches that which is in the book before I go any further. That would always be useful. Question 9. So I think they've written it in a decimal form, but it looks about right. They've got minus 2.39. I think that's about right. Okay, notice how we've only got the one x value though. Not to worry. If we think of two circles overlapping, they could intersect in just one location. But the wording of the question 9b, it says find the coordinates of the intersection points, plural. Now, it could be a red herring. There may only just be 1 point, but let's just see what happens when we use this value of x. So we now need to substitute it into one of the original equations, circle equations. So let's go for the first equation, equation 1. So we are going to have, instead of x plus 2, we're going to have negative 67 over 28 plus 2, all squared, plus y minus 5 all squared is equal to 49. Now, this is going to give us a bit of an evil number inside there. I'm just going to leave it like that just for now and rearrange to get to the y minus 5 squared on its own. So we're going to have y minus 5 squared is equal to 49 minus that set of brackets of minus 67 over 28 plus 2 all squared. And then I'm going to think about how I'm going to get y on its own. So to remove the square, I'm going to square it both sides. But just a little reminder, when we're solving things such as x squared is equal to 10, the result of solving that is actually 2 roots of 10, both positive root 10 and negative root 10. And in this case, it's exactly the same. So y minus 5 will actually equal to plus and negative root of everything they've written above. So 49 minus in brackets negative 67 over 28 plus 2 all squared. All of that with a root over and then plus or minus. So this is where I'm actually going to get two y values even though I've only got one x value. And finally, we just need to add 5 to all of that. So plus or minus the root of everything above and then a plus 5 afterwards. And so our two solutions are going to be minus 67 over 28 or in a decimal form. And then we can either put our positive root with the plus 5 afterwards. I mean, I would work all this out and probably write it in decimal form. It doesn't say to write it in exact form in the book, so we can write it in a decimal form. And then our other coordinate is exactly the same x value, but a different y value, which is the negative root of all that messy business with a plus 5 at the end. So that's how we'd work through question 9b. Okay, having a little look at question 11 in exercise 6e. So find the values of k for which the line y equals kx is a tangent to a circle with center 3, 6 and radius 2. So straight away I'm going to write a circle equation for that. So a center of 3, 6 would have a circle equation of x minus 3 squared plus y minus 6 squared. And the radius is 2, so 2 squared is equal to 4, so that's my circle equation. So I need y minus kx to be a tangent to this circle equation. Now, for it to be a tangent, that means that there is going to be one intersection point. So I need my straight line graph y equals kx to intersect my circle graph in one exact location. So intersection points are found by solving simultaneously. So what I'm going to do, I'm going to substitute y equals kx in place of the y in the circle equation. So I'm going to have x minus 3 squared plus kx minus 6 squared equals 4. So remember, k is just going to be a number here. We actually want to work out the values of k. So k can be a particular number, but it is just a number. So this is actually now an equation in x. And hopefully you recognize that when we're done all expanding, it's actually going to be a quadratic in x that we deal with. And with our quadratic, we can then think about how we can deal with the fact we want just one intersection point, not two and not zero. Let's expand though. So we're going to have x squared minus 6x plus 9 plus k squared x squared minus 12kx plus 36 equals 4. Okay, so it is, even though it looks a bit intimidating, it is just a quadratic. Remember, the k is just a number. So imagine the k is just been replaced with any number we can think of. We're just going to have some x squared terms, some x terms, and then some numbers left over. Now let's just write them in order of x squared terms, then x terms, and then our numbers left over. Remember, for a quadratic, we also want it equal to 0, so I'm going to have that at the end too. So I've got my x squared term leading. I've then got another x squared term with a k squared as its coefficient. I've then got my x term, so I've got a minus 6x and a minus 12kx. And then I've got my numbers, which I can just collect together. So I've got a plus 9 and a plus 36. So that is a plus 45. I then want to take away the 4 from the other side. So I'm going to have a plus 41. And that's going to equal 0. Okay, so if I want to solve this as a quadratic, I know it needs to be written in the form of ax squared plus bx plus c equals 0. Why is it important to look at it like that? Well, reminder that I need just the one intersection point. And if I want a single intersection point, that means I just want one solution for my quadratic. And therefore, b squared minus 4ac, our discriminant from the quadratic, has got to equal exactly 0. So we're going to be using that information, but I need to know what my values are going to be for a, b, and c to be able to use that expression. So I need a single coefficient in front of x squared, which is going to be a single expression for b in front of x, and then anything left over is going to be representing c. So notice my first two terms are my x squared terms. If I factorize my x squared term and just put it at the end, I'm going to be left with a 1 plus k squared in front, and that is going to be my expression for a in the discriminant. If I now look at the next two terms, so I want to factorize an x out of the next two terms. Let me just put a plus after the x squared. What am I left with? Well, I'm left with a negative 6 and a negative 12k. You could actually also take out a negative if you wanted, or even a negative 6 and pull it to the front. That's absolutely fine. But my focus really is just making sure that I've got an x taken out. So that's all I've taken out. Okay, finally, we've got a 41 at the end. Sorry, just to go back, that expression there in front of x, that is going to be my expression for b. My 41 is going to be my expression for c. And it's all equal to 0, so it's in the right format to now use my discriminant. So going into the discriminant then, we're then going to have b squared. So in place of b, I'm going to have minus 6 minus 12k all squared. Take away 4 lots of my expression for a, which is 1 plus k squared, and then c, which is 41. And I need that to equal 0 because I want just one intersection point, just one solution from this quadratic. Okay, now I need to tidy all of this up. So now let's expand and tidy up what we have. So I'm going to have positive 36. 6 times 12 is 72, but I've got two lots of that, so 144. So positive 144k. And then I'm also going to get a positive 144k squared. Right then, the next bit a little bit trickier. Now what I'm going to do here for the next part is I'm actually going to multiply the 4 and the 41 together first. Now there is a minus in front, so mindful of that. So I'm going to put a minus first. Now 4 times 4 times 41 is 164. And then I'm going to have 1 plus k squared afterwards. So I'm going to do that as like the last part, is expand those brackets. So I'm not going to repeat writing out the first bit again, but all of that's going to be the same. I'm not doing anything with that. Now I'm going to expand the second part though. So minus 164 times 1 is just minus 164. And then minus 164 times k squared is minus 164k squared. Okay, now I'm going to be doing some collecting. So I'm going to write over here now. So looking at my k squared terms, I've got 144k squared, subtract 164k squared. So that is negative 20k squareds in total. I've got 144k with nothing else to go with it, so I'm going to put a plus 144k. I've got a 36 take away 164, and that is going to be negative 128. So think about that. That's all equal to 0. So after all this, we are looking to work out values for k. So I've now got a quadratic in k. So you could put this straight into your quadratic formula, or you could play around with it a little bit more. But given that it's all calculator based, it's worth probably just going straight for your quadratic formula. And hopefully it should end up with the correct answers in the end. So what are we looking for? Looking for an answer of question 11. 1.04 and 6.16, hopefully, after all of that. So as I say, yeah, at that point, just very careful. Obviously, we've got negatives in front of the k squared term and a negative at the end. But it's quadratic, and we should know how to solve quadratics from there. Okay, and that's how we go about question 11.